you one other example where this might be applicable. And there's probably many different areas where this is applicable, but one that I used when I was in graduate school, a lot of my work dealt with kids and, you know, things like self-esteem and victimization and bullying. And one of the variables we had was peer liking, how much each kid was liked by their fellow classmates. And so for each child, like for example for Tracy, I could get everybody's liking score for Tracy on a scale of 1 to 5. So, you know, maybe Gabby likes her at a 4.2, or maybe a 4 because it's a 1 to 5 scale. And then Bianca likes her at a 3, and then Chantil likes her at a 5. I'm trying to remember Emily likes her at a 1. Sorry, Tracy, I had to give someone a low score. But then I could average all those scores and get an average score for Tracy on how much she's liked by her peers, the kids in her class. Okay? And so maybe you have our cute little 3rd graders, and Mrs. Alba's class, the average liking score, so now we know how much Tracy on average is liked by her peers, and we know how much Gabby is liked on average by her peers, and how much Emily is liked on average by her peers, and so on and so forth. We've got a score for each of you, how much you are liked by your peers. And then I could average all those scores and get an average class score for how much peer liking there is in this class, right? And maybe this score on a 5-point scale is a 2.5. These kids are pretty tough. They're very, you know, particular about who they like, and so the scores are not all that high. But then maybe there's another 3rd grade class, and their teacher is Mrs. Sunshine. Mrs. Sunshine's class, everything is rainbows and butterflies. And so in her class, the average liking score is a 4.0. Everybody likes each other a lot. You know, kids like each other. All right, so we've got their means, and maybe the standard deviation we found in here is 0.5. And over here, maybe we found it was 0.5 as well, just to make life easy. Okay? And then we were looking at 2 kids, and we're thinking about putting their liking score into our data set, entering data. And maybe Jenny was liked at a 3.0, and Amy, in Mrs. Sunshine's class, was also liked at a 3.0. If we use this as our data when we did our analyses, we really would be comparing apples to oranges without doing the necessary work ahead of time, because it looks like they're equally liked, right? They both got 3.0s. They're equally liked. But they come from different data sets, different distributions, different classes with different means, and actually the same standard deviation, but it could potentially be different, right? So let's see what their z-scores are. If we look at Jenny's z-score, Jenny got a 3, minus the mean was 2.5 over 0.5, okay? So she's 0.5 over 0.5, which is a positive 1. She is like 1 standard deviation above the mean in her class. So she's liked fairly well. Amy, on the other hand, in her class, again, we're going to do score minus the mean. So Amy scores 3 minus the mean, which was 4 over the standard deviation, is a -1 over 0.5, which is a -2. She's 2 standard deviations below the mean in her class. So even though their scores are identical, when we consider their scores relative to the distribution that they're in, or the class that they're in, we find that Jenny's pretty well liked. Amy's not liked very much, right? So again, it allows us to compare these different distributions, individuals within them, and kind of compare apples to oranges because the distributions are different. Okay? Think of it another way. You go to Harvard versus an unaccredited online school. Their distributions might look different. And so you would want to standardize scores before you do comparisons. Does that kind of make sense? Okay. You can stop now.